Good evening. We're back here for another night of cybersecurity with No 404. Today, we're going to be talking about the ABCs of buffer overflows and memory analysis with a wonderful person, Donnie Works. Donnie Works, thanks for coming. And please tell us a little bit about yourself.
Guys, current active duty military trying to transition into cyber, and right now teaching myself a bunch of stuff with a lot of help from this Discord channel and wonderful people here. Um, I kind of put this together as a one way to help myself, and two to kind of I don't know, maybe make it easier for someone else that is just starting out to kind of get a grasp on some of this stuff if you're not familiar with it, like I wasn't. So that's kind of the idea. Am I missing anything, John, or do you want me to just jump
No,
into it?
I think it's a really cool thing. I mentioned that a little bit before in the pre-show banter, but I always find having to teach something is probably the best way to make sure that you learn it at least reasonably well. So it's a great way to go about doing things. So I appreciate that. But yeah, go ahead, man. All you take the floor.
Awesome. Okay, so with that being said, I dropped the link in the meetup text so you guys can just open it up in your own web browser and follow along. I'll try and make it pretty clear where I'm at. If there's anything that you guys need from me when I'm talking, feel free to interrupt. Also, I'm not an expert, like I said, so not guaranteed that all of this is 100% fully fleshed out. I tried to flesh it out as much as I'm able to understand. And I also am talking about a lot of this stuff from the perspective of not necessarily what you're going to read in a book about programming. It's more of hey, this is the general idea. This is a way to kind of visualize it in your head so that it makes sense what they're talking about. If you decide to go and start investigating some of these topics on yourself, it won't be completely unfamiliar, hopefully. So with that being said, that's kind of what I'm here to do. The room that we're working on is listed at the top of the top of this walkthrough. It's a TryHackMe room. It's free for all users, so anyone can do it. It's called Dear QA. So we're gonna start out by going with some basics of some computer science stuff, right? So talking about program execution flow. One of the ways that these are just kind of ways that I think about it. You can figure out whatever works best for you, but maybe this will give you a catalyst. So if you ever seen any of those little games, the marble runs that people create, they're just basically these little tracks that you can create these obstacles, and they do some cool stuff. Some of the tracks change as the marble goes through the track. So the state of the track changes, the features might change. So I mean, have elevators and stuff that will actually change the position of a marble as it goes through the track. Once it hits a certain trigger, it can elevate to a different level. It'll change the path. So there's lots of variables in how the marble can get from essentially its start point to its end point. So that's kind of a an analogy for the way that a computer program executes, right? Another way that you can think about it, and this is kind of one of the first things that popped to my mind when I was reading some stuff on some of this, was thinking of a river system. All right, you have your source. The river does all sorts of things as it goes down and eventually makes its way back into the ocean. And if you want to get super meta about it, you can say, okay, well, it never actually stops. It goes through the whole water cycle and ends up back at the source again, right? So there's that. But it's kind of just again, a simple analogy to help you understand what's happening from the time you start a program to the time it finishes doing what it's intended to do. So here is more of again, simplified version, but this is what I think of as a watershed model. going back to that river analogy of what happens in a program, right? So is everyone good so far? Able to follow along? Like I said, interrupt me. Also, please, if I'm saying something that's absolutely wrong, please correct me. There's definitely some areas that we're going to get into here that I'm still a little fuzzy about. So CPU and RAM. All right, so we're going to boil what the computer's using to execute a program. So you got your program starts in the CPU. It's got to use things in RAM in order to be able to do anything. The program's instructions are in RAM, but it also uses things that are in the CPU. So it kind of like jumps back and forth, and it goes through these different instructions or steps, however you want to think about it, and loading these things called registers, calling different functions, and then it has to go back to and get the instructions for those functions. So it just kind of like, if you want to think about it as like a checklist, it kind of follows that like watershed idea. Like it starts at a point, it kind of meanders around, going back and forth, doing different things until eventually it gets to whatever the intention for all of those set of instructions, like whatever the intended outcome was supposed to be. So simple illustration just to help kind of conceptualize what is going on. For chart is the word. Not sure what you mean. Flow chart. Yeah, it's a flow chart. Behind the scenes. So this is where we're going to get to kind of like, all right, what are those things inside the computer actually responsible for? That was sort of the general idea. What's happening? This is like, okay, so what are some of those things? What are some of those specific components of the computer responsible for? You got CPU, main memory, and system buses, right? So CPU, you got things inside of there like the control unit, the ALU, and these things called registers, which we're going to talk a little bit more about. They basically, you can think of it like working kind of like the way the human brain works. CPU acts as the brain's prefrontal cortex. That's where like your logic center generally is for your brain. Handles decision making, calculations, immediate tasks. The registers are in there, and they're kind of like fleeting thoughts. The ALU handles like logic and reasoning, and then the control unit is what's actually like, I guess, like initiating those. You can think of like initiating those. What's the word I'm looking for? Electric impulses that send like neural messages through your brain. Main memory functions like basically your short-term memory, kind of holds data for quick access. There's a couple of different parts of the main memory. One of them we're going to talk about a little more in depth, called the stack. It's like a to-do list, remembering what is in progress. And then you have this thing called the heap that if you read some more about this type of stuff, you'll hear about, especially some of the more advanced like binary exploitations. It stores information dynamically for later use. It's more akin to like your long-term memory. And then the system buses, you can think of like neural pathways between those different components. So like you got the CPU as your brain, or CPU is like your prefrontal cortex, main memory is like your short-term memory area, and the system buses are just sending messages back and forth between those places so that data can transfer back and forth, or like what you want to do. So they all have to kind of work efficiently in order for, I don't know, for you to function. Otherwise, weird stuff starts happening. That same concept can be applied to a computer, right? So got another little picture I made here to kind of explain or give you like a visual representation of what that might look like. So you got main memory on the side, bottom right-hand corner, RAM CPU with the ALU, registers, and CU. And then I've got some descriptions about the registers in the stack. So registers are located in the CPU. Short-term operations, kind of some stuff we already talked about. Just like little reminders, RAM, main memory, already talked about what that does. And then system buses, same thing. It's just a little graphic representation to kind of cover what we already talked about. And then moving down, these are the registers we're actually going to be talking a little more in depth about today. RBP, RSP, RIP. RBP is the base pointer. You can think of that as like the floor. And RSP is a stack pointer. You can think of that, for right now, think of it as like the ceiling. So we got two boundaries, right? The floor and the ceiling. And then the RIP is an instruction pointer. And that's going to be, you can think of that as like, all right, where to next? So visualizing the stack, I've got another little cool picture I made. Did a lot of stuff in Excel, as you can tell. I was making use of free time at work. So this is kind of what the address structure looks like. And we're going to talk about this a little bit more later too, because it gets kind of weird if this is your first time talking and thinking about this stuff. But essentially, think of a box, like a 2D box. Address structure, addresses are like literally what you would think of like as an address, like this is a location, right? So the lowest address, because they're numbered sequentially, is going to be at what you would normally think of as the top, and then high addresses, or so like if you think number 70 up to 102, lower number, higher number, it's going to be structured from low address to high address, ceiling to floor, if that makes sense. Any questions about that so far? So a buffer, this is going to take place on the thing that we were talking about earlier that I mentioned, the stack, all right? So this is basically a temporary storage place, all right? So in the context of a function being called inside of a program, which a function is just essentially something that a program's doing, right? A function has its own set of variables. So you think of that as like, all right, the function is going to be doing something. It's got a job to do. So the variables are the tools to do its job. And then those variables are giving a temporary workspace. And that is the that space in memory where it's going to be doing the work is its buffer. It exists within a function stack frame. That's like its local work area. So it's got a workspace inside of, you could view it as like its own little section of a building. I don't know if you guys have like different departments where you work at the military. Like if I want to get anything done with administrative stuff, like there's a whole section of the building that's where all the people in admin work. For operations, all the people in operations work in one part of a building. So it's like, you can think of it kind of like that. It's its own like designated work area or workspace. So when a function finishes its job, the thing is that workspace is kind of like on a lease. It gets released back and can be reutilized later. So it's like, hey, we just set up these cubicles for you for today. Once you guys are done with your job, we're going to break them down and something else is going to go there. Now, if you look, I have another little graphic below that says how a function's buffer is allocated on the stack. So this picture is going to come back up, so it's not super important that you understand everything on it right now. But essentially, it's that same sort of box structure we were looking at earlier, going from high to low address. You can see on the right-hand side, it's got start address 70 going up to 118. On the left-hand side, you should see two little red squares. Those individual squares are cells in the Excel file. It says buffer. Those represent those different addresses. So 70 through essentially, like if you look at 70 and 86, 70 goes up to 85, 86 goes up to 101. It takes up that many bytes. So all of that space is the buffer. Then the next address, 102, is the RBP or the base pointer. That's like your floor. And then RET is the ret. We'll talk about that later. On the right-hand side, it kind of breaks down how this is created inside of main memory. So step one, you got to put the RBP, you got to put the floor somewhere. Step two, you got to put the ceiling basically at the same place as the floor. There's no actual space yet. It's just like, hey, here's the foundation. We're just going to throw the roof on top, and then we're going to actually raise it later. Step three, offset RBP. That's like raising the roof. Now you have your space to work. So that is kind of like a very quick and very simplified introduction to some of the concepts we're going to be going over a little bit more in depth. We're going to repeat a lot of stuff. So most likely, if there's anything that's unclear right now, we will revisit it. But if you guys have any questions, again, if there's anything that you want to talk about right this second, let me know. We're going to be talking about a room called Dear QA, like I said, free room on TryHackMe. So this room essentially gives you a binary file called an ELF. So what's an ELF? It stands for executable and linkable file. It's essentially a small program, a binary object file, could be a shared library, could be a core dump. The easiest way to probably think about it is like, hey, this is a like small compact, or not necessarily small compact. It's a self-contained program. So looking at the specs for the Dear QA ELF file, actually, it looks like one of my pictures didn't show up. Wonder if I can see what that's supposed to be. Make sure it's not important. Might be a little important here. I'll drop a screenshot in. I'll drop a screenshot in Meetup text just so you guys can see what I'm looking at. I was working on some formatting earlier and I apparently broke one of the links. All right, let's see. All right, so that should be in now. If you're looking at the page right now and you see something that says looking at program specs with file underscore info.png, that picture is in Meetup text right now. So we're just going to kind of go over what all of that means. There's a 64-bit architecture. So the program's compiled for 64-bit processor architecture, also known as x86-64. It's dynamically linked. So what does that mean? It means that the binary can basically, to make it faster and more efficient and easier, I guess just more compact, is it can utilize what's called shared libraries. libc is a really common one that most Linux operating systems are going to have as a default, right? So if you download this file and it uses shared library libc and you're running a system that has it, which most of them do, then you're good to go. It makes it a lot easier than packing all of that extra information into the program. You can just rely on something that you know everyone already has. Not stripped means that the binary contains debugging symbols and metadata. So that's I'll show you how that's going to be useful to us in a minute. That's things like function names, variable names. I think later on I call them clues. So yeah, if you haven't picked up on it, just yet. This particular binary is for Linux, so we're going to be using some kind of Linux flavored tools. So we're going to check for security features in this binary using a tool called checksec, and I didn't put it in here, but I'm pretty sure checksec is a part of the Pawn Tools library. So if you download Pawn Tools, yeah, it is. It says it right under there. So yeah, if you download Pawn Tools, it will be a part of that package, and you can use it on binaries to see what kind of stuff they've done to protect it or haven't done to protect it. So if you look at the picture, we got no rel-row, no canary found, index unknown, no pi, executable, has RWX segments, and then under script it says no. So what does all that stuff mean if you've never seen it before? So we kind of talked a little bit about the architecture already, saying it's a 64-bit. It's also little Indian. Rel-row, relocatable read-only. That's what that stands for. So what does that mean? It's basically it makes it read-only so that you can not overwrite important stuff, right? So like, if you were able to input something and overwrite an important feature of that program, it would break it. So that's one of those. That's basically what that feature's saying is like, you can move stuff around, but you can't write to it. You can only read it. Canaries, that is a security cookie, and it basically kind of cues in the program that something weird's going on. So if you pretty sure the way that that works is like if you try to put executable code in a certain section, the canary like basically it's like an alarm that like this your code isn't supposed to be inserted here. And then NX non-executable, that's basically means you can't inject shellcode in particular parts of memory. So Windows World, they call it something a little bit different, but it's the same thing. Basically, is data execution prevention. It's just basically saying like, hey, you can't execute things in this portion of memory. Pi, position independent executable. So that's basically randomizing the address structure so that when you go to try and find where certain things are at, it's not as predictable. So a more advanced version of the stuff that we're talking about today is called return-oriented programming, which is kind of dependent on knowing where things are at. So like, hey, I know that this function is at this address, so I'm going to lead it to that function so that I can do something else. If you don't know where that important function is, you're basically having to play a guessing game of trying to get whatever you're injecting into this program to essentially get lucky and find the right spot to land on, which is incredibly difficult because there's so many addresses, right? So by stack, it says that it's executable. That means that the stack has permissions, executable permissions enabled by default. That allows code to run directly from the stack. So that's kind of important. But that's only if there's no NX security feature enforced. So the stack can be executable, but if you have NX, it kind of negates that. So that's important to note when you're looking at that. Sorry, reading Nordgaren's note here. Yeah. Yeah, that seems like a much better way to phrase that. Thanks for sharing. RWX, it says that it's present, indicates that program has at least one memory segment that is readable, writable, and executable. And then stripped, we kind of talked about that. This is not. That means that those debugging symbols, function names, metadata, that stuff might still be in there from when it was programmed, and then left in there once compiled. So, okay, yeah. So that's a lot of words, right? All right. That's why I made this a write-up, so that if you don't understand it from me stumbling through saying a lot of that stuff the first time, you can go back and read it here. Not all of that stuff is going to be super important right this second. And if it is, we're going to talk about it again. Like I said, we're going to loop back to a lot of things. Testing the waters. So we're going to run the program and just see what it does. All right. So we got this program. We downloaded it from TryHackMe, from one of their rooms. And we're just going to run it and see what it does. So if you can see the screenshot, I put // dear QA, and it starts running. It says, welcome, dear QA. I'm sysadmin. I'm new in developing. What's your name? So I give it some input because it's asking me for my name. So I write my name, Donnie Works, in there. And then it returns a formatted string that says hello, and it basically spits my input back at me. Donnie Works. So if I said something like, my name is You're Dumb, and it would say, hello, you're dumb, and that would be really rude, so that's why I didn't write that. Seems pretty simple, but this program takes user input, returns formatted string, right? So let's start analyzing this a little bit. So some common commands for, when you first get a binary like this, besides just going through and seeing what it does, like dynamically or like in real time, you can run strings command just to see, is there anything in there? Did someone leave some words in there that might be helpful for me? Are there any of those, like, if it's not stripped, maybe there's some interesting stuff in there. There'll be like clues, right? So I ran the strings command. You can see this really long output here. I highlighted some stuff in fuchsia because that's the color that I like to highlight stuff with because it pops. So I highlighted scanf, exec ve, /bin/bash, hello, %s. And then down towards the bottom, you see vuln and main. All right. We'll come back to some of the top ones. Vuln and main. Those like immediately popped out to me, especially main, because in most source code, there's going to be a main function. In fact, I think I'm not 100% on that. I think in C, there has to be a main function or the program won't even run. So essentially, it's going to be something that once you start the program, it's going to be something that that it's looking for in order to actually start doing anything. So main is a really common function name. Vuln just seems suspicious and obvious, but this is an easy challenge on TryHackMe. So like, yeah, they're giving us some clues. So I'm gonna investigate that in a minute. NM, actually didn't know about this until I started writing this, and it's another common Linux utility. It can be used as a debugging tool. Kind of does the same thing, but it does this. If you look at the picture, it's got a nifty little address bar on the side. So all of these different things that it's showing you, it shows you the address that they're located at. So that's pretty cool and helpful. And look at that. It has the address for main and vuln. And then it also has this little symbol T beside it, and you can see beside some other ones, B, T, D. That's basically just telling you what those things are, or what they like, how they function in this program, what they're being used as. We're not going to talk too much about that right now. Those are basically just two like dimmies that I wanted to make sure that you guys saw, so that you can have something to use. And then as we go along, I'll show you some of the more the tools that I'm using more heavily. Another one is obj dump. Honestly, I don't use this too terribly much because I'll show you what I'm using in a minute that I think is like pretty robust. But some people have preferences, so it's good to have some options just to see what might be more intuitive for you to like figure some of this stuff out or start understanding what you're seeing more. Because the one I'm going to show you, when I first looked at it, it was honestly pretty overwhelming to me because I had no idea what I was looking at. So it took a while to go through and figure out like what all the different sections were until later I realized it basically tells you. So obj dump, we're going to use the TAC T switch so we can dump symbol information, which is kind of what we've been looking at, right? A bunch of symbols in the files. And here we got the addresses for main and vuln. So you got that main address. And I'm just going to shorten these for the sake of brevity, 406C3 and then 400.686 for vuln. So those are addresses that we're probably going to be using. The one with all the zeros is a 64-bit address. This is 64-bit architecture. That's why it looks like that. I'm using more of like the 32-bit. Not even that. I'm just using a shortened version for the sake of being able to talk about it in a clear way. If you notice, both of these functions came from the .text section. So we talked about that sort of at the beginning. What's in RAM? There's the source code, and the .text section is a part of that source code, and it contains what we're talking about right now, some functions. Disassembly. So obj dump can also act as a disassembler. So the source code is languages typically like C. You can think of stuff like if you've done any work with Python, it's more of like the higher level language. And then assembly is kind of a middle ground between, it's a lower level language, but it's like a middle ground between what the machine understands and still being readable to humans, right? So disassembly is essentially this program is being run and your obj dump is in a sense like reverse engineering what the assembly instructions would be. So that's kind of the thing. You'll if you start reading about some of this stuff, you'll read about assembly, and then you'll see some people talk about disassembly. It's basically just talking about it as being a program being run and then it turning the machine code back into assembly, or like some sort of approximation of it. So we got like our higher level languages, stuff that we're actually writing programs in, most likely, unless you're like super brilliant. Assembly, lower level language, a lot harder to read, a lot harder to write, a lot more tedious. And then you got like the actual machine code, which some people reference as shell code or op code. You'll hear those different things depending on kind of the context that they're talking about usually, but it's pretty interchangeable as far as I can tell. So we have we disassembled the .text section, and I have a picture of it. You see all those yellow words, stuff like push and then blue RBP. So you got push RBP, move RBP, RSP, move EDI. If you see that picture, just above that, where it says Kali at Kali, THM, DQA, obj dump, I have the command that I ran to get this output, and I'm kind of break down kind of what that command means in obj dump so that you can understand like how we're getting this output and what format it's giving it to us in. So TAC D, or sorry, the switch for the D switch, however you guys want to say it. When I say TAC, if you guys don't know what that means, it's just a dash. That's militarism. Sorry. So TAC D, disassemble, TAC capital M. Those are your options. Here we're specifying Intel, which is basically the syntax that it's going to provide us for disassembly. we would probably touch on that again later. There's multiple types of syntax. It basically just has to do with like the order in which you're reading the order in which you're reading the operands, I guess. Yeah, AT&T syntax backwards. It has like percent symbols and stuff in it too, like for talking about like relative addressing. I'm not super keen on it. I've gone from reading some of these books, I've kind of started to recognize it, but this is definitely a lot more straightforward, I feel like. And then we got the section equals. That's just identifying, hey, what part of this program do we want to take a closer look at? And we're going to look at the .text section because that's where main and vuln are. Start address, same thing. Tac start address equals. All right, where do we want to start this dump? So we're going to choose the lowest address of the two that we want to look at, and then it will dump out everything after that. You could actually take a stop address too, but since we don't really know where these functions stop, I just basically cropped the screenshot so that you just see vuln and main. But if you were to run this command on your computer, it would actually dump out way more stuff in this. It would fill up your screen. But these are the two sections that we're going to be focusing on. So that's why I just cropped that and didn't worry about a stop address, because intuitively, if you were looking at this, you probably wouldn't know where the stop address was unless you're like really good at guessing. So, all right, phase 2. So we're going to talk about Ghidra code browser a little bit. It's useful. What pseudocode is essentially like a high level. It's like basically it's giving you like a high level representation, or you can think of it as like paraphrasing to a certain degree what the code is. It's not necessarily the actual code. It's just like, hey, based on what is happening inside your machine, this is what we think. Like, this is like how we're going to represent it, and it does a pretty good job. In this program, the source code is C, so it's going to spit out sudo C. Yeah, I've got memes. If you guys like memes, I've got lots of memes.
Memes are good.
I'm embarrassed to admit how much time I spent on the memes for this walkthrough, but I'm like super invested in all of them. So if you don't like them, don't tell me, please. Just kidding. So this is what the pseudocode or the pseudo C for the main function in our program looks like. And I'm going to break this down. Yeah, NSA noises, dude. Love that meme. So good. All right. Main. So char local 28 with brackets and 32. What the hell does that mean? Well, if you are familiar with C, you'll probably be like, dude, why are we talking about this? But if you're not familiar with C, like I wasn't, like 2 to 3 months ago, I started off with like, what does that mean? And basically what this is it's just saying, hey, this is accepting characters. Local 28 is just like a symbolic name, right? Local meaning it's a local variable. 28 is actually hex. We're going to be talking a lot in hex as we go on, hexadecimal. So it's 40 actually, but it's represented in hex, so it says 28. So it is a variable that is 40 bytes long. And then in parentheses, you have 32. So 32 tells you that the buffer occupies 32 contiguous bytes in the stack's memory, right? So that's actually going to be the important part for us, because that's what we're going to be talking about more in as we go on, is the stack and the buffer. we want to know how big it is because we need to know that for other reasons later. So 32 contiguous bytes. What about the other 8 bytes from the 40 bytes of the whole variable? Like it said it's 40 bytes long. Why are we only paying attention to the 32? Well, when it's compiled, it puts in padding automatically to make everything fit to the system's architecture. So basically, Ghidra, as far as I can tell, is just accounting for that. And it's not necessarily going to be important for us with what we're doing. But that's how you can kind of break that down. You also notice that ISOC99 scanf, the scanf is the important part here. That is a function. And what that does is, like we saw in our program, it asked us for our name, and we gave it our name, right? We typed it in, we gave it input. So the scanf is a function that reads that formatted input that you're giving the computer, and then it's going to take that input from, essentially your keyboard, and it's going to put that and store it on the stack. So a note about scanf is that it's considered insecure because it doesn't do certain it doesn't have certain security features that are like automatic, right? It doesn't check and validate the user's input. It doesn't make sure that what you're trying to enter isn't too long for the space that it has to put what you're trying to enter on the stack. So that's kind of a big foreshadowing there. One other note that I put here is that vuln and main, they're not referenced. Vuln is not referenced in the main function. So that's interesting. Why is there a function that, when we look at main, never gets called, right? So the main function's purpose is kind of to it's kind of like the supervisor of the program. It's like, all right, I need all of you to do this, this, and this. But vuln's it's in the building, but there's no accountability for it. So that is interesting. There's no clear programmed connection to it. It just exists there for some reason. So we're going to take a closer look at Ghidra's pseudo C for the vuln function. And I highlighted what I thought was important here, the exec VE and the call to bin bash. So bin bash, if you're not familiar, is basically opening up a shell in a Linux environment, or one of the ways. Opening up a bash shell specifically. Exec VE is a system call. So that's using privileged access to execute another program, right? It's I have a definition here. So system call is a direct request from a program to the operating system. So you might have heard the word kernel thrown around, to perform a task that the program itself doesn't have permission to handle directly. So this program, main, doesn't have permission to open up a bash shell, but exec VE does. So that's how, vuln doesn't have permission to open up a bash shell, but exec VE does. So exec VE is basically called upon in this function to open up a shell. Yes, born again shell. What else? Kind of talked about exec VE. Yeah, please interrupt me if I say something incorrect. Don't just laugh at me, guys. All right, so what's our goal here? We kind of alluded to it a little bit. We're giving the program input. There's no one saying that, hey, you can only put this much input in here. There's no one at the door checking, make sure that it's not too big, right? So our goal is to control the program flow. we know that there's a program or there's a function inside of this program that executes privileged or uses privileged access to open up a shell, which in hacker world is usually the goal. So that's what we're trying to do, is we're trying to say, all right, well, main doesn't go to vuln, but somehow we want to get from main to vuln. So if you go back to the river analogy, that like watershed model, the program's going to be flowing somewhere. It's going it's going from point to point, right? We want to control where that goes, and we want it to end up on vuln so that we can open up. That's the gist of it. Thought we were just trying to get people to all right, phase 3, working with pond debug or pond dbg, however you want to say it. This is built off of a common command line debugger called GDB, and it's I'm like almost positive that it's like affiliated with Pontools, but I'm not sure. Can't say it 100%. But this is a pretty robust tool. It was super overwhelming for me to look at it first because I had no idea about what I was looking at. Hex was unfamiliar, assembly was unfamiliar, C was unfamiliar, and this tool is just like, hey, look at all of those things at once. And I was like, all right. So we're going to run the program, and we're going to set what's called a breakpoint. So if you want to run a program with PondDBG, you just download it and then run GDB, and it will be incorporated into that library. Or it'll be utilized as a library, so it'll kind of automatically go to pond debug. So we're going to run it. We're going to set what's called a breakpoint. That's basically an instruction, we're essentially giving it an address or an instruction inside the program where we want to pause execution. So we want to just basically stop that flow real quick so we can see what's going on. So we're going to set a breakpoint at main and run the program. And if you want to do that, I've put the commands there. It's like break main or break the super long 64-bit address, or you can just use the shorthand address I was using, and you can even shorten break to just B. And as you go through, like, you'll learn the little hacks, I guess, of using pond debug. So if you look at the screenshot, you can see where I ran the command at the very top, and then it tells you, all right, we have a breakpoint 1 set at this address. And then right beneath that, you see where the little caret and red pond debug are. I typed run, and then it runs the program, and then we hit our breakpoint, and it pauses and shows you what's happening at that point. So if you look at this, there's a lot going on. Pro tip, look at the blue lines that literally tell you what all those things are, and don't like stare at the actual data in between trying to just figure it out like I did. Make life easy for yourself. So I highlighted this little arrow by 406C3, and you can see it says main because that's the name of the function that we're in. And then beside it, it's got some assembly instructions, push RBP. So that's essentially that little arrow or caret on the far left-hand side beside the 0x43’s. That's where your RIP or your instruction pointer is pointing. This is the next thing the program's going to do, or the next instruction it's going to execute. So it hasn't yet. It's just pointing to it. And like I said, RIP, you can think of it as like, all right, where to next? That's what it's telling you. That's what we're doing next. Or that's where we're going next. So next instruction, push RBP, talked about that. So what does that do? It's going to mark the base of our function stack frame. So basically we're going to say, hey, this is where the floor is going to be for this this thing that we're doing. So stepping through the program. So besides just setting breakpoints, you kind of have to know where things are at in order to set breakpoints. So if you don't know where those things are at, you can step through the program and just kind of see what's happening slowed down, basically going, like pausing at each point of execution. So we're going to use commands like step and steppy. Some other useful commands are ni and si, or ni, si. So step does, shorthand is just S, like B is shorthand for break. It executes the next line of code at the source level. And if the current line calls a function, it will step into the function stopping at the first instruction. So basically, it's going to go wherever the next instruction leads it. And if that leads it into a function, it's going to go there, but it's going to not execute that function. It's just going to stop at the first step. Steppy is a little bit different, a little more granular. It executes the next single instruction at the machine code level. So that's where we're talking about the difference of like the assembly instructions. So like push RVP as example, as opposed to like some of the pseudo C that we were looking at earlier. That's a little bit more high level. It's got a lot of assembly. Each one of those steps in C has a lot of assembly inside of it to make it happen. So you can think of Steppy as just like the more granular level, where we're actually going through each individual machine code instead of like what we would read as like a an instruction in like human readable language, if that makes sense. Useful for stepping through assembly instructions, especially when debugging binaries without source code. So yeah, alternative to if you don't have the source code. NI, next instruction, executes next instruction, but then it does not step into the function. So that's useful because like if I did this actually with this binary before I got a little more proficient with Pond debug, was like getting way too granular and going through every single instruction wherever it led until I saw something that looked like, what's that? Don't necessarily have to do that. Sometimes it's useful. And then step instruction executes the next instruction, steps into the function, calls when it's encountered. It's similar to Steppy, but emphasizes stepping into function level details. So we're going to use step. We're going to make it simple because this is a pretty simple program. But those are there. If you guys have some other binaries that you want to like go through and practice, or in this one, go back and look through and just kind of like go through the motions yourself and just see what it looks like and see how it changes. So this is at step 2. If you want to think about it like that, the output, if you see where it's highlighted, it says main +1. That's relative addressing. So it's basically at wherever main is, 463. If you look at this address, it's 464. So 3 + 1 is 4, right? Pretty straightforward. Relative addressing, let's get Dorian, do you know the other name for that? I forget. Offset. Sorry, blanking out. Okay. Yeah, so it's using like offsets to reference where certain instructions are at, or relative addressing. That's really common. So this instruction, move RBP to RSP. And I promise we'll talk about some more of the nitty gritty of other things that are going on in this window. But right now we're just going through kind of like stepping through and seeing what the instructions at the like assembly level say. So we got the RIP pointing to move RBP, RSP. So what that means is it's going to set the base pointer to the same location as the stack pointer, which means our floor and our ceiling are at the exact same address. There's no space in between right now. So there's not really a workspace yet. It's just like getting ready to set up that workspace, if that makes sense. And then we move on to step 3. For some reason, I didn't highlight this one, my bad, but you can see the green letters in the middle. 467 main plus 4 sub RSP comma 0x20. Again, that's in hex. So 20 in hex is actually 32. So we're actually making a space of 32 bytes for this stack frame from the RBP to the RSP. So that space in between the floor and the ceiling is 32 bytes long. That's our workspace. And that matches up with what Giger was telling us earlier when I said it has 32 contiguous bytes in memory. So dots are lining up, facts are checking out, computer's not lying to us. It's not time for Skynet to take over yet, apparently. So RIP pointing here, allocate 32 bytes. I give you the little hexadecimal to decimal conversion. So allocating the buffer, and this is what it's going to look like pre-user input. So that point in the program where it's like, what's your name? This is what that looks like at the in disassembly. This is where we're at. So if you look at the little caret or the little arrow, the equal sign of the caret, that indicates the current position where RIP is, relative address of +4. So it's pointing to that thing that we just talked about. Like that's what's about to happen. We're about to allocate a buffer. So essentially, once you give it input, the program is going to make that buffer, and then it's going to put whatever you have as input into that buffer. So I think I talked about, yep. All right, cool. So I said we come back to this next picture, and it would probably make more sense. So I have like not the same addresses here. I got the simplified, easy to look at addresses, 70 to 102. It's easy to tell that that's 32 bytes, right? You can see in the middle here what the address is, kind of like, it's just reminding you they're really going to be in this architecture 64-bit address or 16 hex digits. What that looks like is super long and cumbersome. So step 1, we talked about push RBP. We're going to place the RBP on the stack. Step 2, we're going to then move RBP RSP to the RSP. So they're co-located. The ceiling and the floor are together, no space in between. And then step 3, the one we're about to execute, it's going to then offset the RSP or move the ceiling up away from the floor and give us that buffer space over here. All that makes sense so far?
Sure
Sounds like it. Sick. All right. So this is kind of a simplified representation of what's going on. Info registers is another good tool. So you can go down at any of these points and just kind of get like a different picture of what's going on, just formatted a little bit different, I guess. So this is what they look like at when the instruction's pointing at main +4. So it's pointing at that sub RSP 020. Actually, no, it's not. Sorry, I think this might be after it's executed. 1 second. Nope, this is prior to executing. All right, cool. Yeah, I highlighted it. You can see it. RBP, RSP, you can see same address. So I'm going to reference these as like the last 4 characters, DC10 or DC10, instead of 7FFFFF. You know what I'm saying? So you can see, okay, they got the same address, right? That makes sense for step 2 that we talked about. Move RBP, RSP. It's exactly what it did, moved to the same address. Our RIP is pointing to a different address, main +4, 467. So RBP, RSP are co-located, same address. We executed, I think that's the wrong, oh no, yeah, we executed step 2 and of the main function. And so info registers after executing the buffer allocation step that we talked about, the sub RSP with the 32 in hex 0x20, prior to user providing input, we're going to set breakpoints, break star main +8 or this address right here. That's so that we can kind of look in and see what happens like right before user input gets dealt with. So we've made the buffer, but the user input they haven't done anything with it, if that makes sense. So now you can see RSP has a different address, and you can go online or download like a hex calculator and confirm that if you subtract DBF0 from DC10, that's 20 in hex or 32 bytes. Which I did a lot of because I was not super familiar with hex and was like trying to make sure that I wasn't going crazy when I was going through and figuring some of the stuff out. So RSP is offset by 32 bytes. Did the little math thing. It looks weird. Formatting's still messed up on this. That's great. Love it. Cool. Yeah, for sure. So like once you get I guess more familiar with hex, it actually does it is a little bit easier to like conceptualize certain problems. But it takes a little bit of getting used to. And if you've learned to like looking at binary or anything, like how that works, the first time you look at it, it's a little bit like it's just new. So you have to get used to it. So we're going to talk a little bit more about the stack and then this thing that we're going to be doing, buffer overflow, kind of really, beating a dead horse here just to make sure that it's clear. So we talked about the stack as a section in memory for temporary storage of variables, like the one that we found in Ghidra, local 28, the one that's creating our 32-byte buffer. So the way that the stack works is a last in, first out principle, LAFO. So you can think of it as like stack of dishes, right? If you are putting them down one at a time, the first one is going to end up on the floor, and then the last one that you put in there is going to end up towards the ceiling. So the top is pointing to, if you look at the little picture, it's pointing to C, right? That's the last plate that we put on the stack. Now, if you start taking them off the stack, the top is adjusted. It goes down towards the floor. So that I like making diagrams when I'm thinking about like little pictures and stuff when I'm thinking about concepts, because when I was reading about some of this stuff in some of the books that I have some of them listed, I think, at the end of this. They don't really do that, or at least most of them didn't, the ones I was reading. So it's like purely just like reading words and trying to make sure that I understand how to read English, I guess. But yeah, I found these types of things to be pretty helpful. So when people say the RSP points to the top of the stack, they don't necessarily mean the highest addressed in memory. All right, because like we said earlier, it's when you look at it visually, the lowest address is actually like spatially, like on a vertical y-axis, is like what you would think of as higher, right? So as the function runs normally and ends up reaching its ret instruction, which is basically saying, all right, this function's done, we're going back to what we were doing before, or picking up where we left off, is probably closer to accurate. The RSP is what it's going to do. If you see that little top of the arrow, that's essentially the RSP. It's pointing to the highest address or the highest plate in this stack currently. So if we've taken any plates off the stack, the RSP is going to be adjusted closer to the RBP or closer to, you can think of it as the floor. So yeah, why that was confusing for me is because the stack grows downward. So when you start with when you're building a stack, you start with the floor, and then you put the ceiling visually lower, but it's visually higher, but it's a lower address. So it's kind of counterintuitive because we typically visualize upward progression as like from a grounding point, right? Whereas the address structure is, ceiling to roof, low to high address. So then you take the RBP, which is at the highest address, also the floor is the way we're thinking about it. And then the top is sometimes at the bottom, low address, or you can think of it as the bottom of the stack because we've taken stuff off of it, so because it moves. So now I got all these funny memes to let you guys share in the confusion that I had and laugh. So using simplified addresses, again with the 70 to 102 thing, kind of just providing extra visual representation of what's happening. We got oh, by the way, this, I guess I was reading AT&T syntax when I was building this, because this is what AT&T syntax looks like on the right-hand side where it says stack growth. So you can see it's very similar to Intel syntax, but the %RVP is just like, that's instead of just saying RVP, that's how they reference it. And you can see here, instead of move RVP to RSP, they reverse the order. So it's actually move. It's like outside in kind of thing. Move RVP to RSP. So you can think of it as like action, the origin, destination. The other way? Is that backwards? Is it really? Did I confuse that? Okay, my bad. Thank you for bringing that up. That actually probably clarifies something I was confused about later. Yeah, okay. So what Nordgaren was saying is, yeah, I had that backwards. So this will be like action, basically your starting value and then where you're moving that value to, right? And this is basically just representing the stuff that we already talked about: push RVP, RSP, sub RSP 0x20. So we're creating that buffer. This is the space allocated for the variables, and then you got your RVP is that highest address, but we're thinking of it as the floor of our stack for right now, for something we'll get to in a second. And then this is essentially the function that we're looking at here. So this is pre-overflow input. There's stuff in here, but it's not anything that we've put in there. So when we're going to write user input into the buffer, we're using the scanf function, and it's going to basically read what our keyboard's typing, and it's going to be written from low address to high address. So from 70 to 102, you can think of it as like that. Overflow behavior. So this is what's essentially happening. So like our buffer's 32 bytes, right? We're going to put 33. I'm going to put a 33 byte name into my input. What's going to happen is it's going to start where it's supposed to and start writing. And this is just simplified, right? Like this is byte 1, byte 2, byte 3, et cetera, et cetera. And so you get to, all right, here's the end of our buffer. 33 is actually going to overwrite what was written in our RVP. So we've corrupted whatever data we had here by inputting more data than we were supposed to, but there was no security feature to stop us. So we just entered 33 bytes, and that byte corrupted the first byte of our RVP address. So this is no longer, this data, whatever it was doing before, is no longer going to do that. It's now invalid. So the cup analogy, this is kind of how I thought about it when I was first thinking about buffer overflow. RVP is the floor, like I've been telling you, right? So it defines a boundary, essentially the base of the stack frame. It serves as a reference point for accessing local variables. And what I mean by that is what's the thing that we were talking about earlier is relative addressing. It's basically like from this point, This other thing that's in, or this other variable inside of this function is this distance away, right? So it's like, all right, this is our home base. We know how to get to point B from home base. Buffer is the cup that's going to be holding the input that we're going to be giving the program, and the cup's only so big. The overflow is like if you put too much data in there, it starts spilling over. So right here we have our, if you look at the picture, we have our scanf feature is going to be basically writing all of that data that we're giving it, or writing that user input into the buffer. And we're going to give it too much, so it's going to spill over the buffer and start overwriting the RBP, spilling all over the RBP and potentially other stuff. This is what it's going to look like post overflow input. So again, like this is not to scale. This is way too many bytes, but like this is the buffer space. We inputted a bunch of stuff, which is 41 is hex representation of the letter capital A. So we just put in a bunch of A's, and then RBP here, we put in some B's. 42 is the hex representation for capital B. And then I have a little note here about the return, basically what it does. It's before the stack's even built, this return address is stored on the stack, usually right after RBP somewhere. And it basically allows the function to return, once this function is done doing what it's doing, it's done with its job, and is all cleaned up and like ready to go home for the day. The return instruction sends it back to, it's like a bookmark, like we're going back to what we were doing before, or what we were reading, the instructions we were reading before, picking up where we left off. So that allows us to like clean up from this function and go back to where we were before we called the function. So you might be thinking, all right, well, the return instruction is still there. We've overwritten the base pointer, but the return instruction is still there. So why are we not going back to the original function, what they call the caller function? So the reason that happens is because the reason that the return instruction falters here is because the stack pointer has been corrupted and now points to an invalid memory location. So remember when we said as we input data, the RSP is being updated. So the RSP was here, or RSP was like here. We started writing in data. The RSP is essentially moving as each byte gets input into the buffer. So it's being updated, right? Because that space has been utilized now. It's no longer, it needs to be reserved there for something to be input. Something's already been input. So RSP is going to update, and RSP is going to point the stack to basically something that doesn't exist. So it's going to create confusion. So I got a little analogy here for that I call heliochopters, because that's the background I come from. So you can imagine a pilot flying at night, right? Over glassy water, stars reflecting, clouds, whatever, right? That situation creates an interesting effect that can be very disorienting, because everything looks the same. Like the water is like a mirror, so like you look down and it literally looks like you're looking up at the stars. So when pilots are flying, they rely on something just besides like their eyeballs to know where they're going, because your eyes can deceive you. So there's a phenomenon known as a false horizon. So this is kind of like a not like a up is down, down is up immediately type situation. It's more like a gradual, like, oh, I didn't notice that this was happening sort of thing. So they're just flying along, right? And they're looking at what they think is the horizon. And it might actually be something like a cloud bank. and the cloud bank might actually be lower than the physical horizon. So if they think they're looking at the horizon, and for some reason their instruments, so in this scenario, that would be like the security features, I guess, in the program that prevent us from doing stuff we're not supposed to do. So the instruments in the helicopter are supposed to prevent the pilots from doing stuff like this. And if they're not working, they could just look at that cloud bank or look at that false horizon and start flying towards it and never know that they're basically pointing the helicopter at the ground, because everything looks the same. So there's no visual cues to say, hey, dude, you're flying towards the ground. And the instruments aren't backing them up and giving them like confirmation feedback that they're doing the right thing or telling them that they're doing the wrong thing. So this is called controlled flight into terrain. The pilot has no idea that they're disoriented and drives straight into the water. So that's basically what we're causing the computer to do, where it's just going along doing what it's built to do. And we're kind of like messing with the direction that we're leading it, and we're leading it into ultimately what could be, in the case that we just saw, an invalid memory location, which would lead to a segment fault or a crash the program, which isn't super useful in all scenarios. But we're going to talk about something that could be a little bit more useful. We're going to redirect that that execution flow to something that's going to do something for us. So we're going to lead it to that phone function we talked about to open up a shell. So that requires a little bit more finesse than just putting in more data than the buffer can handle, right? We have to actually end up somewhere. So that's kind of the distinction and analogy of basically what we just talked about is overwriting the RBP. It's just going to crash. So now what we're going to do, a little raccoon meme, had to throw a raccoon one in there for the homies. We're going to overwrite the return address. So this is just talking a little bit more about the stack. I feel like we've kind of talked about it a lot. You guys can go back and look at that if you want to. Pretty much all the stuff we've already covered. So in this program, the stack frame we've talked about goes from DBF0 to DC10. And if you look here in this little screenshot, we've got a little bit more than that. You'll see at DC28, we have the main address. So that is our return address, and that's going to lead us back to supposed to lead us back to the main function, or the start of the main function. So here you can see some things that we've talked about, RSP, RVP, yep, talked about that. Okay, yeah, so stuff on the right side the reason I put this note in here is because like all the stuff that you see, you're seeing it on the stack and in the buffer. Like, so if the buffer goes from here down to here, and there's all this stuff in here, that doesn't necessarily mean that that's a part of that function or does anything. Earlier, we talked about reallocation of memory space after a function is completed. So this could be just basically leftover data that is yet to be overwritten. All right. So when you look at this, you kind of have to have a little bit of discernment. Not everything you see is going to be like immediately useful. Some of it might be leftover from previous functions, or just that space in memory hasn't been overwritten yet. So just a little aside. Look at the stack frame viewed 1 byte at a time. I don't know why I ended up doing this, other than I was like, I'm going to be super, super granular for no reason. But anyways, here it is. Talk a little bit about how you can examine some things in OnDebug. We're going to examine the memory contents of the stack, and we're going to look at it. So you can see DBF0. I added DBE8. That's the padding area, just so you can see that there's nothing in there. It's just uninitialized space. But DBF0 is where our stack starts, goes up to DC10. That's the area we're going to be kind of focusing in on. And this is byte by byte. So like each one of these little bytes is technically a memory address, right? So you can see it like jumps up. That's because each one of these is an address. So this is like the start address and then next address, next address. So it's got data in each of these addresses. So X / examine memory contents at a specified address, which we will specify here. 72 is the number of entries that you want to display. B is the memory and bytes. So I did the byte by byte format just to be super extra. And then X, display it in hex format because that's what the program's spitting out to us a lot. So it's just easier to be consistent so you can recognize things. So the bytes here appear in reverse order. That's because Intel architecture is Little Endian, which basically just means like an example here, we said that the main address was 406C3. So if you look here, we've got the 000406C3. That's just how it stores the information. And then Big Endian would be the opposite, or like what you would think of reading from left to right. So it's just a distinction to be aware of because you'll see it differently in different architectures and in different challenges. But really, like it's not that huge of a difference. Like it's just once you recognize it that it's both a possibility, then you start to, I guess, pay closer attention and recognize addresses more easily or data more easily. Knowing that it could be written both ways. So we're going to run the program, put a break at main plus 80, and that is the point where we actually give the user input. Indius came from the book Gulliver's Travels. I'm not familiar with that, actually. I was thinking of it. I think someone made an analogy of like it ends in kind of thing, like which end goes in first. Oh, okay. Yeah. I guess that makes sense. Huh. Cool. So we're gonna running the program, setting a breakpoint. Not really important how I got to this breakpoint. Spoiler, it was super tedious, and I did the whole thing where I was going through every single assembly instruction unnecessarily because I didn't know what I was looking for yet, but you don't have to, so that's cool. So this is where our breakpoint is at. We're going to run it. This is the point where we provide user input. So this is what the computer is going to look like once we give it input. Remember, I gave it my name, Donnie Works. So you can see here, RBP is at DC10, RSP is at DBF0. Our instruction pointer is pointing to this random address that took me forever to find. And then you can see that RAX is holding my name. RSP, oh yeah, this is what I meant to say, like at this point. So the blue lines, super important. This shows you what the registers are doing, or what's in the registers. This shows you the disassembly. This shows you the stack. This is backtrace. We're not going to talk about that, but because we're not using it really yet, or in this walkthrough. But yeah, it's super easy to like figure out what all that stuff is because it gives you labels. So yeah, took me a lot longer than it probably should have to recognize that. So looking at the registers, super extra byte by byte again. If you guys look at my name or my profile in Discord, I actually have my name in hex. It's X64, X6F, blah, 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 all the way up to X73. So if you look we're going to examine our stack here, DBF0 to DC10, and we're going to see X64, X6F, X6C, all the way up to X73. That's my name because that's the user input we got. So cool. I put my name in the buffer. So that's 12 bytes. We have a 32-byte buffer. So how many bytes we got left to get up to RBP to start overwriting it? Let you guys roll that over. Fuzzing. Filling the buffer with junk is known as fuzzing. We're basically just confirming it's vulnerable. We kind of just confirmed that we could put stuff in there. More just showing you what it looks like when you do put stuff in there. But now we're actually going to confirm that we can overwrite it using this more robust tool, PondDBG, which we kind of showed earlier, but this is going to be a little bit more of like a step-by-step. So this is the command that I'm using. I'm going to give it 32 A's and 18 B's. I gave it a little more B's than necessary just so that we can see like what it does. So this is the command I used. R is just short for run. Then the 3 left pointing carets is basically just saying, hey, whatever comes after this, we're going to input that in once we run as input once we run the command. So you put the little, I forget what the dollar sign's called, but the command prompt, I guess. And then inside these parentheses is Python, which is just basically saying, hey, we're going to be doing this using the Python library. And then tax C is for, I'm going to run some code. And then in parentheses here is going to be my code. And I'm using a print command, which is just going to print 32 A's and 18 B's. So basically, exactly what we said. I'm going to give it input 32 A's and 18 B's. This is just a way to do that in PondDebug without like running the program and then like having to like go through the process of interacting with the actual program. Is just like giving all the information that you want to give it up front and then running it, and we're going to see what happens. So it says, hey, I'm sysadmin. It kind of gives you the standard out, like what you gave it. And then we have a segmentation fault, which we mentioned earlier. That's going to happen. We're going to crash the program. And then you can look at what's in the registers. RBP contains, remember earlier we said 42 was hex for B. It gives you the ACII, but or ASCII, or however you say it. It gives you that. And then RSP is pointing to this address, DC18, which was like kind of in between our RBP and our return address. And it also has a bunch of B's there. So, and then our instruction pointer is pointing to some other thing. So this is the disassembly. This is what that looks like. We're at the red instruction, but the red instruction has a bunch of B's in it. So it's like, what? That don't exist. Because 42, a bunch of B's is not a valid memory address in the computer. So closer look at the registers, being super extra again with the byte by byte. You can see A, et cetera, until it starts doing B. And what do we say? RBP was at DC10, overwrote that. And then DC18, which is now where our stack pointer is pointing, overwrote that. And then it even kept going a little bit. So it overflowed like way more than we've talked about up to this point. It went past the RBP and almost went up to our main address up here, the return address. So notice, I think I just talked about that. All right, cool. So now we're going back to the how do we actually control this? We're going to redirect this program to do something different. We're going to talk about the phone function. We have the address already. We got that at the very beginning from strings or something like that. Any things you chose, set a breakpoint. disassemble main, you can see, hey, that's our return address, 472F, which we saw up here somewhere. Where was it? RIP, that's where the instruction pointer is pointing, right? So, and then we set our breakpoint. We're going to run it. We're basically going to give it all our junk data or our fuzz data, and we're going to try and make it end up at this address, the 400.686. Here's that super long Python command to do that. I kind of break it down. You guys can go through and read this if you want. I'm going to skip over it for right now because we're running over a little bit. But basically, this does the same thing. It just sends the junk data, and then it tacks on that address, and it does some formatting to make sure that it ends up in the right format. So we're going to test it. So this is that long Python command that we used and directly inputted to running pond debug in this program with Dear QA. There's our breakpoint at 472F. Here's what RBP looks like. Here's what our instruction pointer is pointing to, 472F. And you can see here, that's our vuln function. So that's cool. We're getting there. RSP, stack pointer pointing to DC18 has the vuln address 400.686 in there. Okay, just talked about this. Look at the stack. Okay, yeah. So the point of this image here is the RIP pointing to the return instruction, which we talked about. This instruction takes the value at the top of the stack, or where RSP is currently pointing. It's pointing to 400.686. It places it into the RIP. So this is getting a little more granular, like what's happening. It places it into the RIP register, which is where we're going to go next. And then the CPU tells it to jump to that address and execute the instructions found there. And that address leads us to vuln, so it's going to execute whatever happens at vuln. We already talked about what that is. That is opening up a shell. Cool. Closer look at the stack. We got that 400.686 here. 400.686, little Indian. It's beautiful, Marty. Recap. This is everything that we've done so far. You guys probably remember. It's been a long, arduous journey, but we got here. We overwrote return address directly with the vuln function. Cool. So when red is executed, what's going to happen? It's going to pop the value at the top of the stack, which happens to be pointing to where we want to go. And then the RIP register is going to update this value, and it's going to directly go there and do the thing. So once we fully execute this, run it without breakpoints, because we did set that breakpoint just to see the registers and see that that vuln address was going to be there. Kind of confirming what is going to happen as much as we can without actually just being like, send it. The program should redirect the flow of execution to a function that was not originally supposed to be executed at all. So cool. We got from main that wasn't really supposed to do much except say hello to us, and we got it to go to this other cool function that does something way cooler by redirecting it, and now it's going to open up a shell for us. And that's yeah, pretty cool stuff. So now we got to write some scripts. So this is like the quick part of all of this pre-work that we did to get to this point. Now we're gonna execute this locally. So remember, we downloaded this from TryHackMe. So basically we're going through and like doing it in our lab in like an environment that it doesn't matter if we crash the program. If the program crashes, we can just restart it because we control it, right? So we're going to make sure that this is actually going to work as intended before we try and send it to the TryHackMe server, or the one that's the vulnerable machine that's set up to be attacked. We're going to do it in our own environment so we can make sure it works. Once we make sure it works, we just have to send it to the right place, and then we should be able to get the goal of this room, which is a flag. So breaking this down a little bit, there's different ways to write these scripts, different sort of syntax you can use. This particular one that I went with is kind of from the Pawn Tools side of the house. Before this, I had been mostly working on like Windows rooms, so I wasn't really using Pawn Tools. So this was kind of a learning curve for me. So I went through and provided like a breakdown of what all this stuff is for all of us. And it's not a whole lot different. It's just like some of the things are, some of the syntax is just a little bit different. So some standard stuff, we're just telling it that, hey, this is a Python file. So we're going to be using that library. So interpret it as such. We're going to import everything. That's what the little asterisk means. It's the wildcard. We're going to take in all the stuff from Pawn, which is just the shorthand name for Pawn Tools. We're going to import that entire library so we can use all that stuff that it has, all the tools that it has, if we need it. Context here, basically, we're just telling the script, hey, what you're doing right now is reading an ELF file or a binary. And the name of that file is Dear QA. So it's going to run /Dear QA in the context of an ELF binary. So it's going to load the binary as an ELF object, allowing access to its symbol section. So it can read things like the functions names and stuff like that. P, this is where it gets a little bit different than I was used to. P, process binary, starts the binary as a local process for interaction. This is pretty much the same. I came up with something that was like probably a little more visually pleasing to look at for the payload. I have some other walkthroughs on my GitHub that you can go through and see like the different ways I've written some of these scripts. This is a little bit more cumbersome with the payload plus equals payload plus equals. There's some other cool tools out there that you can use to like, or just like using Python itself to like format the payload that looks prettier in my opinion. It's just, but it's not really that important. So here we're saying the payload is 32 A's, and then we're going to add to that 8 B's. So I changed it from 18 to 8 because 8 is actually all we need. Because after 8, after the 8 bytes at the RBP address, we're going to start putting that vuln functions address, and P64 is packet in basically format it in 64 architecture. So this is the address 400.686, but it's going to make sure that it actually packs the address in a way that the computer can read it as a 64-bit little Indian format. So that's just something to note. That was a little bit different than I had been used to seeing. This is also the sending and interactive p.send line. So it's just sending the payload that we crafted up here, which is these lines, payload A plus the B plus the address. And then interactive, so switches it to interactive mode, so you can actually interact with whatever happens after you exploit this process, right? So I sent it, and then I got a command prompt, which you can see down here in red. So that tells me, oh, this is what I named it, local.exploit.py. So you can see how I ran it, Python 3, just saying, hey, using Python command line interpreter, this is the file that I'm executing. It goes through, you can see the program starts running, welcome, Dear QA, says all the stuff, what's your name, and I say a bunch of gibberish with an address sort of tacked on. It says, congratulations, you have entered the secret function. And if you go back and look at the Ghidra pseudocode, that's actually built into the vuln function. So that's how you know that you got there. But I also know because I got a command prompt, so I've opened up a shell. So Now we're going to test it on the real thing. If you haven't used TryHackMe before, super easy. You just go to the room, join the room, and then you're going to download these task files to go through all the stuff that we already did. You're also going to have to download what's an OpenVPN config file so that you can access their network of servers to be able to utilize them. And then you're going to have to run that so that you're connected to it. It's usually like sudo OpenVPN, whatever your username is, .ovpn, and then you're gonna have to put in your password or whatever. But that'll give you basically permission to access their network of vulnerable machines that you can start playing around in their rooms. Start the machine. It'll take a minute, give you an IP address. That's basically what you're gonna connect to that's the vulnerable machine or where it's located. It gives you 2 hours, plenty of time for this challenge. Now we have the IP and the port service it's running on. I think it said it somewhere. Yeah, running on port 5700. So this is what the remote exploit script's going to look like. See you later, MSUper. Thanks for coming. Thanks for sticking around. Sorry it's taking so long for me to talk so much. Remote exploit. This is the difference, right? So basically all the same stuff. Payload. Make sure we got the same payload. We're making the distinction that it's going to be remote, connecting to a host and a port. We define the host and port here as variables. This was my address. Yours will be different. They kind of rotate through. This is the port. And then P send line, payload, P interactive. So not a whole lot different. We're just connecting remotely versus sending it to interact with a binary on our own computer. There's a binary running on their server here. So breaking down what's changed, you send it, it's going to work, spoiler. And then here you can just go see, I really didn't have to do that much to find the flag. Once I sent this exploit, I got the command prompt, so I knew a shell had opened up. I have access, I ask who I am. We're just some random user, they named CTF. Asked what the ID was, it starts giving you all the privilege information, what groups they belong to, that sort of thing. So like all the standard stuff you'll see in a lot of the rooms. LS, let's see what's in this current directory here that we're at. It's got, spoiler, the source code in C, and then the actual binary that we downloaded earlier, and then something called flag.txt, which is what we're probably looking for, because if you're new to CTFs, that's generally what a lot of them are geared towards, is like looking for a flag, which is really just it's like this right here, cat flag.txt. That just is short for concatenate or concatenate. I can never remember that, but it's basically just printing it out for you. And this is what a flag looks like. There's usually 2 curly brackets. Whatever the name of the CTF is usually at the beginning here, and then they have some like cool little like leet speak phrase in here, and you just have to find where that text file is, and then you submit it, and that's how you get the points. So all I did was copy and paste this into the answer on the page, and I completed that room. So pretty easy, right? As far as like actual execution, it's just a lot of kind of prologue information that you need to get through in order to be familiar enough to know what you're looking for and how to find it, which is a lot easier said than done with some of these types of challenges, because like there's so many different areas to be familiar with, which a lot of them seem like super kind of overwhelming at first, but they're really not. They can be, but like, don't let that stop you. If you take it like one piece at a time, eventually you'll start building up like these little foundational blocks, and then more and more stuff will start to make sense. And I'm not saying that as if I get binary exploitation now, because I certainly do not. It is, I'm, like I said, just started even looking into it like 2 to 3 months ago. So I've got some books listed here at the end. and like just some resources that I found really helpful. Go and read through those. They're kind of dense sometimes, but like don't be afraid to just like look at a paragraph and read it and walk away from it until it makes sense and then come back. Because like I legitimately had to do that, or read it over and over again and just sit down and be like, okay, what language is that? Oh yeah, okay, it's English, so I've got a starting point, and then just go from there. And then I also had some other. Oh no, I deleted it. Wait, did I? Oh, it's just poorly formatted. Sorry, this markdown thing. All right, Obsidian failing me, but it's okay. I still love it. So here's some topics that'll be helpful, I think, and we kind of hit on some of them. If you want to get into more of this stuff, just learn a little bit of assembly language. You don't have to be a programmer, just to get familiar with it and sort of understand, be able to read it. C language, you'll see a lot of that. Python is great if you're already working on that. It's super popular, helpful in a lot of different areas, like the scripts that you just saw. Computer architecture, just kind of talking about CPUs, main memory, like getting familiar with that stuff. If you want to get like a little more into the weeds, return-oriented programming is like a little bit more of an extension of the stuff that we just talked about. The stuff that we talked about was stack buffer overflow. That's like the basic version of this. And then like there's a lot of cool ways to do this sort of stuff. Lots more to learn. If you're that kind of person that likes constantly being into stuff and learning new things and just like going down rabbit holes, which is 100% me, do it. Go down the rabbit hole, man. It's fun. I'm in the Discord if you guys have any questions. I know it's super late. I'm sorry. So feel free to drop off. If you guys have any questions for me, I'll hang around. If not, you can always DM me if you have some questions, or if you just like want to give me some additional resources. That'd be fucking cool too.